Okay, welcome everybody to the APS Physics Journal Club. I am Jeff Eldredge of the University of California at Los Angeles, and I will be serving as the moderator for this discussion. So I'm pleased to introduce today's presenter, Alan Kaptanoglu, who's a fifth-year PhD student at the University of Washington. He's been studying at the intersection of plasma physics and fluid dynamics and machine learning. So he was previously an undergraduate at Stanford, where he focused on theoretical physics, and he's already won several awards for his work, including last summer he won a Best Student Presentation Award at the Sherwin Fusion Theory Conference. And he's going to be pursuing a postdoctoral position at the University of Maryland with Dr. Matt Landerman after he finishes this year. So without further ado, Alan, go ahead and take the floor.
Thanks very much.
Sorry, before we start, I need to remind you some basic things. Please keep yourself muted during this discussion, if you can, when you come in. And if you have questions, please put them in the chat room. And at the end, we'll go through the questions, I'll moderate them, and I'll invite you to ask your question yourself. Okay, thank you very much. Go ahead, Alan.
Thanks very much for the introduction. Just making sure everyone can see my slides. I sound normal, my internet connection's okay, it's all set. Great. Okay, so yeah, thanks Jeff for the introduction. Thanks very much to Physical Review Fluids for the invitation. Today I'm going to be talking about promoting global stability in data-driven models of quadratic nonlinear dynamics. And I know that's a mouthful, but we'll go through the jargon as we go along here. This is work done by me and my collaborators here at the University of Washington, including my advisor, Steve Brunton, Chris Hansen, Jared Callahan, and Alexander Ravkin. If you are interested in these methods and learning more, we have an amazing GitHub repository, SINDy, where you can reproduce everything you see here, plus much more in several other papers. So please take a look at that if you're interested. And with that, let's get started. So the big picture summary here, the motivating question is, can we build nonlinear stability theorems directly into system identification? If you don't know what system identification is, I apologize, but I have a brief slide on the next page where I'll briefly describe this. But that's going to be the goal. It turns out Schlegel and Nowak have this 2015 JFM paper where they provide conditions for what are called POD-Galerkin models of fluid flows to exhibit global boundedness. And this global boundedness basically means no matter what initial condition you start your fluid system at, it's guaranteed to always fall into some region. It's never going to give you some unbounded, unphysical trajectory. So this theorem is really great. It can actually already be used as a diagnostic for reduced order models. So if you have some fluid flow system, you get some POD-Galerkin model for it, you can actually use this theorem to check, is that model globally stable for any initial condition I can throw at it. So this is really great. We actually take a different direction. So instead we promote these stability conditions directly during the model finding process itself. Rather than checking if the model is stable at the end, we build the stability condition into the search. So what this looks like for instance, the Lorentz attractor is you have this, their version of global boundedness is basically the system exhibits what's called a monotonically trapping region. That's the sphere that I've illustrated in blue. And now when you have any initial condition, way out here or way out here, it's guaranteed to fall uniformly and asymptotically into this blue trapping region, and then stay there for all time. And because all trajectories fall into this region and then stay there for all time, you have global boundedness. There's no crazy initial condition you can choose that will give you some unphysical, unbounded trajectory. And importantly, within this trapping region, you can have these regions of positive energy growth, where I plotted this region in red for the Lorentz attractor. And in fact, this region is exactly what keeps the Lorentz attractor on this nice limit cycle, rather than converging down to a fixed point. So this is the sense of stability we're going to be talking about in this paper. If you want a little more detail comparing and contrasting different forms of stability, I do have an extra slide at the end, so please ask about that if you're curious. Before showing how we build that in, let's just briefly review how sparse system identification works. So I'm going to be talking about a specific system identification method called SINDy. This is based off my advisor Steve Brunton's 2016 paper. Many of you have probably already seen this before. Basically, you have some simulation or experimental data. It's evolving according to some underlying governing equations, which for the Lorentz attractor, we'll pretend we don't know for a second. Then you just take some measurements of the data. We take measurements of x dot, y dot, and z dot. We arrange that into some matrix big X dot. So here are your measurements arranged as columns. You've taken these measurements at some time snapshots. And now what you do is build a candidate right-hand side here that describes the evolution of this data in time. So you're trying to take some data and then build a system of equations that describes how that data evolves in time. And what you do is you build a candidate library of possible terms. So here we choose up to fifth order polynomials in x, y, and z, although you can put in whatever functions that you want. And then we also have this coefficient matrix, which just chooses how strong are each of the coefficients in these models. So that's basically you're building a bunch of candidate models. What we do is we solve an optimization problem to solve this problem. And we ask for the set of coefficients such that we minimize the difference between the left-hand side, your data, and the right-hand side, the candidate model. So here you're just fitting the data. And then we add what's called a sparsity prior, which just tries to zero out as many of these coefficients as possible. And that's really nice because you end up getting these sparse, interpretable, parsimonious models that tend to avoid some of the overfitting issues with other methods if there's noise and measurement error in the system. So we can solve this optimization problem for Lorentz, and you might get something like this, where, so for the first equation, instead of -10 and 10, you get -10 and 10 up to some numerical precision in the coefficients, and similarly for the other equations. And now with this new system of equations you've directly discovered from the data, you can actually evolve the system with some new initial condition, and again, find a nice attracting set here. So, so that's very brief how system identification works. I do want to point out that even in this noiseless case, you do get these small numerical errors in the coefficients. And so we would actually like to build in a way to produce models that are globally stable for any initial condition, even if there are these errors in the coefficients, which if there's enough noise, will eventually start giving you models that produce unbounded trajectories for some crazy initial condition you can throw at it. Oh, okay. So how do we actually promote globally stable models during these types of system ID methods? So the first thing we're going to do is I'm going to illustrate the trapping theorem from the Schlegel-Nowak JFM paper. Basically, they do a POD-Galerkin projection onto the Navier-Stokes equations. If you don't know what that looks like, I'm going to give a super brief review. Basically, you take some spatiotemporal measurements of the velocity field, and you expand it in an orthonormal basis like that from the proper orthogonal decomposition. So you get some expansion in these temporal and spatial modes. You substitute that expansion into, for instance, the incompressible Navier-Stokes equations, and you get what's called a POD-Galerkin model, which describes the evolution of these temporal POD modes. I've also included this extra constraint, which is saying that the nonlinearities in the system are energy preserving. And this extra constraint is required for the theorem to hold. So we are assuming a little extra about the fluid system, but in fact, many fluids and magnetohydrodynamic flows satisfy this constraint nicely. So this is not so restrictive. Still following the JFM paper, now what we do is we define this matrix AS, which is the symmetrized matrix L appearing in the POD-Galerkin model here. And this state vector M dotted with this QIJK tensor. So we can make that definition. We have so we can define this AS, and now the theorem is that there exists a monotonically trapping region at least as small as the ball, centered at M, with some radius Rm that they provide estimates for, if and only if the real symmetric matrix AS is negative definite with eigenvalues ordered in this way. And so once again, so for visualization, what they're saying is, if you can find an M such that AS is negative definite, you're gonna, there is guaranteed to exist this blue monotonically trapping region, and therefore you have global stability in the system. So the name of the game then is basically searching for this vector M to find a negative definite AS, right? So we can actually build that into system identification in the following way. So we're again solving that optimization problem I showed from the previous slide, but now we have the same first two terms. So we're still fitting the data. We're still trying to zero out as many of those coefficients as possible. And now we've added two new terms. The first term just encodes that the nonlinearity is energy preserving. So it encodes this constraint right here. And we need to explicitly put this in as a hard constraint because the theorem relies on this, quality of the model. And then the last term we put in is this lambda1, this largest eigenvalue of AS. And we put it in as a loss term to be minimized as we search over these vectors M. So basically we're searching for a model, but at the same time, we're trying to search for an M and push this matrix AS into the space of negative definite matrices, so that the model that we come up with, we can actually basically get models that not only fit the data, but are actually provably stable for any new initial condition you can throw at it. So for the next slide, let me just briefly say, if you just use the first three terms with no minimization over M, we call this constrained SINDy. And if you do the full minimization, we call this trapping SINDy. And I'm going to compare those two methods with or without this last term on the next slide. So what I'm showing here is, again, the constrained SINDy method, so without that last loss term, and the trapping method with that last loss term. And then at three different sparsity thresholds. So we're increasing the amount of sparsity in those model coefficients. And I'm showing four different testing trajectories. And basically the takeaway from this comparison is that this extra loss term in the trapping algorithm actually nicely gives us some robustness to noise, and it correctly sort of gets the right limit cycle for the Lorentz system, despite the fact that there's as you can see, lots of noise added to the system. The constrained SINDy actually usually gives you a stable model, as you can see here, but it's clearly giving you the incorrect stability. It's not giving you this limit cycle you expect. It's actually sometimes giving you these weird fixed points that don't fit the data well at all. So that's a nice indication. Not only we can get these globally stable models, but actually we can also get potentially some additional noise robustness. And then we also do this for a simple magnetohydrodynamic problem. So basically, this is a Fourier-Galerkin model for the first three components of the velocity and magnetic field of an MHD model. And if you're interested, the equations of motion are here. This is actually a Hamiltonian system that doesn't quite fit the requirements of the trapping theorem, but actually still our loss term allows us to minimize the change in energy and actually correctly model these fully Hamiltonian systems. And what I'm plotting here are these state space pictures where, for instance, V1 with V1 is just a straight line. It's the same variable. V1, V2 gives you this nice geometric Hamiltonian structure, and similarly with all the other combinations in the state space. What I'm showing in black is the fit with trapping SINDy, and the blue is training data, the red is testing data. So in both cases, the trapping SINDy model almost perfectly preserves the Hamiltonian property and correctly reproduces the dynamics. Of course, this wouldn't be a fluids talk if I didn't show the von Karman vortex street at some point. So I'm going to compare the ground truth, the POD Galerkin model, the analytic model from Noack et al.'s 2003 paper, and then our trapping SINDy model on the bottom. And I'm going to speed this up a little bit because it's a little slow. if I can. There we go. So basically, our trapping SINDy model correctly gets the transient timing right. It's then going to overshoot a little bit and screw up the vortex wake for a moment, but then it relaxes, fixes the overshoot, and correctly gets the vortex shedding for the remaining time. Meanwhile, the Pioti-Galerkin model is just starting the instability, so it's gotten the transient timing a bit wrong. And then you're going to see that it never quite gets the vortex wake correct. It still gets some shimmering, some numerical artifacts. The big takeaway here is we can outperform these Pioti-Galerkin models, and we can basically give guarantees about, if you give me some new initial condition, this will still give you bounded trajectories and the vortex shedding that you expect. To wrap up, we use the Schlegel-Nowak trapping theorem to promote global boundedness during system identification. We illustrated strong performance on incompressible flows with energy-preserving nonlinearities, including, importantly, systems with transients like the von Karman vortex street. There's a lot of future work to be done here, including connecting the Schlegel-Nowak result and our algorithm to alternative low-dimensional bases. So everything I've shown you here, we did with the POD basis in a particular expansion of that velocity field. But there are many different low-dimensional bases that are being used today, including many nonlinear bases from manifold learning, autoencoders, and Koopman operators. And so that'd be a very interesting way to go to sort of build these stability guarantees into different bases. And then also a lot of work to be done connecting with data-driven algorithms that already search for Lyapunov functions. And what these algorithms do is you're doing system identification. So you're trying to get the governing equations from a set of data, but at the same time, you're trying to discover a Lyapunov function that gives you some local or global stability of that model you're trying to build. So this is a similar sort of thing where you're trying to build in stability properties.
Like it's not down. Just
so you're trying to build in stability properties directly into the system ID method. So that's it for me. Thanks very much for everyone who came, and I'll be happy to take questions now.
Thank you, Alan. That was great. So we have the floor open for questions. I see one already in the chat, and if you have other ones, please enter them there. Eric, I'm going to invite you to ask what you're calling a dumb question. Doesn't seem so dumb.
Okay, unmuted. Yeah, I just had a simple question, which is about your trapping SINDy approach for looking at the von Karman vortex street. I was wondering how many degrees of freedom you had in the trapping SINDy approach, right? There was 9 modes in the old POD approach. How many degrees of freedom did you use?
So there's a different answers for different versions of that question. So we build both a 5D trapping SINDy model and a 9D trapping SINDy model for all the 9 original modes in the Nowak et al. Paper. The trapping SINDy method itself has 3 hyperparameters, and you've got, so it has more than we would like, but you can sort of scan these and play with these based on the data. You can also build some automated things to actually like fix your hyperparameters based on the norm of the data.
Sorry, and are these hyperparameters like the things that appear in your energy or your minimization problem?
Yeah, so let me go back to the...
Like your ADA, right?
Yeah. That's right. So this is the minimization we're doing. And so we have a hyperparameter lambda here, which determines how sparse do you want the coefficients to be. We also have this hyperparameter eta here, which is basically allowing us to turn up and down how much we want to promote stability into the model. So if you turn eta very, very high, this loss term basically disappears and you just reproduce the normal constrained SINDy stuff. So anyways, we have the hyperparameters there. And then for the von Karman vortex street, specifically for the 9D model, if you're trying to fit a quadratic library for that system, it turns out to be a 330 dimensional a non-convex optimization problem. So,
okay.
it's pretty ugly, and it's also a very ill-conditioned problem because the von Karman vortex street exhibits these harmonics. So when you're doing regression, it's like hard to tell what the difference is between harmonics. So yeah, it depending on the problem, it can be a hard optimization problem to solve. Thanks for the question.
Thank you.
Can I ask a follow-up before we get to the next question? How long does it take to train that model then, the 5-mode one?
It's very, very quick. So it's so the solution when lambda equals 0, actually you can get an analytic solution. And so for lambda equals 0, it's extremely quick. We can immediately do this alternating algorithm to get the solution. When lambda is not equal to 0, this is a very convoluted non-convex problem. And so we actually make a convex relaxation of this problem and then solve it with CVX pi. And because we're solving it with CVX pi is not like, optimal for particular problems. So it can be slow when lambda is non-zero.
I see. So getting the sparsity is the challenging part.
Yeah.
Yuan Young, you want to ask your question?
Yes, just quickly, do you standardize your data before you do the SINDy least square solve, or?
So for everything in the paper, we did no, as far as I know, we did no standardization or mean subtraction or anything like that. It is the case that often this does improve the performance. So one thing that actually helps a lot, if I go back to this page, this candidate library of terms, depending on the norm of each of these columns, some columns might be very, very like large in value, and other columns may be very small. So one thing you might do is normalize each of these columns to unit norm. And that usually helps a lot in actually identifying the dynamics, because there's not like columns that have much stronger value than all the others. So yeah, I mean, you definitely can improve on a lot of these models by doing that sort of pre-processing.
But you didn't have to. I guess that's what you're saying in your case, in your examples.
I don't believe so. So it might be the case with the von Karman vortex street with the POD modes that we get. So first of all, the shift mode for the POD, you have to compute from the simulation. And then the other modes, I'm not sure. I would have to check with my collaborator, Jared Callahan, if we do any mean subtraction or anything like that. But not that I'm aware.
Okay, thank you.
They're by definition kind of mean 0, since we computed the POD modes from the mean subtracted flow.
Thanks, Jared.
But I think you're correct that we didn't normalize it. And that does help in some cases. In some cases with POD coefficients specifically, it may not make physical sense because they have the interpretation as kinetic energy. So it just depends on your application.
So part of this exercise is to find M, which is the mean of your mode, your coefficients, right? Is that true? So in the case of like POD, you've already done the mean subtraction, so it identifies 0, I guess, as the center of the. Is that it's kind of trivial maybe in that case? I don't know. You're looking for this ball, right? Where things are drawn into, and the center of the ball is what you're looking for, right?
Yeah, it's a little tricky. So we do assume that that there is this steady state piece which you can subtract out of before fitting the model for these AIs. Mm-hmm. And then you have this sitting around, so you can add it back in for the reconstructions later.
I was confusing things, I think, a little bit. Can you mute yourself, please? Oh, sorry.
There is this other aspect of and that's probably, I don't know, Alan, you could speak to this better than me, but there's this aspect of this trapping theorem where you're basically shifting the center, you're doing a coordinate transformation, and that's what kind of lets you construct this Lyapunov. Yeah, the M. So the M is not necessarily 0, even if you do mean subtraction.
I guess I was curious about the meaning of M, and then like in the case of the vortex shedding.
Yeah, so I think the way you want to think about, for instance, starting with the Lorentz system, is the attractor, the center of the attractor doesn't sit at the origin. It actually sits at some offset place. And so if you just tried to build the trapping region around the origin, you would actually get a worse bound. You'd have to like expand it pretty far to enclose the entire thing.
I see.
And yeah, so M is basically where the sort of optimal origin of your trapping region is. So you want to,
small region.
yeah, exactly. And that allows you to sort of center around the correct region where the fixed points and any attracting sets are. Yeah.
Okay, so maybe it's harder to understand it physically what it means. Okay.
The specific case of the cylinder in this paper, they kind of explored a little bit, and it turned out that M was all zeros except for the coefficient corresponding to the shift mode. So
Okay.
in that case, it's easier to understand as being related to that mean base difference. In general, yeah, it's a little bit more difficult to interpret.
Arcane. Okay. See, well, in the absence of other questions, I'm going to ask my own since I came prepared. So, Alan, what can you say about uncertainty? For example, you noise up your data when you train it. So, what about the uncertainty of your predicted model?
In terms of what exactly?
Well, for example, you've got this noisy data, which means that you have, you're trying to uncover some underlying, signal in there that is, basically the mean of, of your noisy result data, right? But there's also implicitly an uncertainty bound on that too, I think, right?
So, yeah, I'm not quite sure what you're asking still. Basically, you're right that in these noisy cases, you can actually get models which are quite far from the true underlying model because of all the noise. Right. So actually, many of these models don't like get super close to the correct coefficients. They actually build like slightly different models that still get the attracting behavior, but actually have, some different coefficients on many of the terms.
So you measure the sort of goodness of your trajectory from your model versus some underlying truth, right?
Thanks. Yeah. So yeah, we have two main error metrics. One is basically how well does your model fit the training measurement data you took, and we normalize that so you can sort of worst case scenario it's 1. And then we also have the metric where you can actually look at each of the individual coefficients you took. And in the case of something like Lorentz, we know the true coefficients. And so we can actually just find what is the error in each of the coefficient places, and then, average that or what have you. There is also, in some places, we do use the error on the simulated trajectory data. But this is a really hard thing to get right, even in totally clean Lorentz data, because Lorentz is chaotic. So even if you get like 8 decimal places on the Lorentz coefficients, eventually it'll incorrectly lobe switch when it shouldn't, and so you might get a high error even though your coefficients are extremely close to correct. But yeah, those are some metrics you might use to validate how well you're doing.
Other questions? Okay. That takes us up against the time 9:30 or 9:30 my time. Sorry, you guys are all in different times. So going once, okay, going twice. I think that's brings us to the end. I want to thank Alan and his co-authors for presenting their work. Without further ado, have a great day. Thank you.
Thanks a lot, everyone.
Thank you, Alan. Thank you, Jeff.
Thanks, everyone.
Bye, everyone.